In this video, I'm going to give you a walkthrough of setting up the PyTorch mobile runtime in an Android project. To follow along, you'll need Android Studio 3.5 or higher, and you'll need to have Gradle installed.
You should also be using PyTorch 1.7 or higher to take advantage of the mobile optimization processes shown in this video.
PyTorch offers native runtimes for iOS and Android, allowing you to bring your machine learning app to mobile devices. Including the library in your project is a one-liner, but there is more to do getting your model set up for best performance on mobile.
In this video, we'll demonstrate how to set up your Android Studio project to include PyTorch Mobile, how to export your model to TorchScript, PyTorch's optimized model representation, how to optimize your model for best performance on mobile, how to include your model in your project, and how to call the model for inference from your Java code.
For this demonstration, we're going to build an image classifier into an Android app. First, we'll create the project. I'm going to create an empty activity app. I'll set the target language to Java and the minimum SDK version to 28. In the build.gradle for your project, make sure that JCenter is listed in your repositories. Now we'll add PyTorch to the build.gradle for the app. This will bring in versions of the PyTorch Android library for all of the Android APIs for ARM and x86. It will also bring in a library from TorchVision that contains helper functions for converting Android in-memory image types to PyTorch tensors.
Now I'll show you how to prepare your model to run on the PyTorch mobile runtime. You'll want PyTorch 1.7 or higher for this workflow. First, we'll need a model. For the mobile project, I have a pre-trained model ready to go, but I'll be demonstrating the optimization process on a custom model here to better show how you can apply this to your own models. This is a simple model containing a few common layer types. First, there's a section with a convolutional layer, a batch norm layer, and a ReLU. These are wrapped together in a torch.nn.sequential. This is a common practice to organize submodules within complex models, but we'll be doing it here to show how organizing your layers this way impacts layer fusion. After that, we have a linear layer and another ReLU. The forward function strings these layers and operations together in a pretty straightforward way. Note that I've also added quantization stubs. You'll need to include these if you want to use quantization-aware training. Now we'll instantiate the model and put it in eval mode. This is an important step as it turns off computationally expensive gradient tracking and disables training-only features such as dropout layers. Looking at the structure of the model, it looks like we'd expect. All the layers we created, in the order we created them, with the first section wrapped in a sequential block. Our first optimization step is to fuse layers. Layer fusion combines multiple PyTorch modules into single operations, improving speed and memory footprint. Only certain ordered combinations of modules are allowed. For full details, see the docs at pytorch.org, but for this demonstration, we'll be fusing the convnet, batch norm, and ReLU, and we'll also fuse the linear layer and its following ReLU. We have to specify the layers we want to fuse by name. Note how the inclusion of our first three layers in a block impacts the names. We have to prepend the name of the sequential block with a dot to each of the names of the layers we want to address. This pattern would continue if the blocks were nested more deeply. Linear layers are not included in a block, so we just address them directly. Our linear layer is not included in a block, so we just address it and its following ReLU directly. Now we run fuse modules. Looking at the fused model structure, we can see that in each fused section, the first layer now encompasses the functionality of the whole block, and later layers are converted to identity layers, essentially no-ops. The second step is quantizing your model. By default, PyTorch models use 32-bit floating point numbers for weights and computation. Quantization converts the model to some narrower bit width number, usually an 8-bit integer. PyTorch offers three workflows for quantization. Dynamic post-training quantization quantizes the model's weights ahead of time, but handles quantization of activations dynamically at runtime. Static post-training quantization quantizes both the weights and activations ahead of time. Quantization-aware training simulates the effects of quantization during training for added accuracy. These three quantization methods have trade-offs associated with them, which are discussed fully in the quantization documentation at pytorch.org. Here, we'll demonstrate static post-training quantization. To quantize our model, first we'll get a quantization config, here Q and npack. Note that this configuration is specific to ARM processors. This is what you want for mobile devices, but means you won't be able to run the model locally on an x86 processor after conversion. Next, we prepare the model for quantization. That sets it up for calibration. The calibration step is optional, but recommended. To calibrate the model, you'll need to run a representative set of data through it, much as you would for a training loop. This helps find the correct 0 point and scaling for the float32 to 8-bit int conversion. Finally, calling torch.quantization.convert will do the actual quantization of your model's weights and activations. If you don't perform a calibration step, you'll get a default 0 point and scaling factor, as we did here, if you note the warning text. Our final step is to convert the model to Torch script and optimize it for the PyTorch mobile runtime. Torch script is PyTorch's optimized model representation, containing both your model's computation graph and learning weights. It allows the PyTorch just-in-time compiler in the PyTorch mobile runtime to perform runtime optimizations during inference. The PyTorch mobile optimizer makes further adjustments to the model that are specific to PyTorch mobile. Once we've converted the model with torch.jit.script and optimized it, we can save it. The file we save here will be the one we include in our mobile project.
We'll need to add some resources. I'm going to add my model file. Of course, you should use your model exported to Torch script, and an image for the model to classify. I'll put them in a new assets folder. I'm also going to add one source file that just contains a string array of the human readable labels for the classes my model is trained against. Next, we'll put together a UI. I'll have an image view to show the image we're classifying, a button to start the inference process, and a text view to show the result. Now, watching me set up UI constraints is not very educational, so let's speed through this bit. Now, let's fill in the code for our activity. We'll make a couple of private members for our image and our model. Next, I'll add a helper function that gets the absolute path for an asset. PyTorch Mobile expects a file in the file system for the model. Next, we'll fill in the onCreate. It's a bunch of code, so let's take it a piece at a time. First, we get the bitmap and model objects. We wrap these in a try block because if there's an issue with either, we can't run the app really. Next, we'll fill the image view with the image, and we'll set up an on-click listener for our button. Inside the on-click listener, we're going to convert our image to a PyTorch tensor. We're going to pass that tensor to the model for classification and receive the output. We'll find the model's most likely class for this image and its human readable label. And finally, we'll report that label in the text view. So let's run it now and see it work. And there's our cat. We press the infer button, and sure enough, our model thinks our cat is a cat. Success.